Hello, and welcome to the first online lecture for rational choice theory. These lectures will contain some background material. We may go over some theorems that we didn't have a chance to prove in class. We may spend some extra time going over proofs, or we may work out some examples. So this first online lecture will discuss some background material. I want to make sure that we're all on the same page when it comes to talking about relations and preference. All right, so to begin, we need to first define the Cartesian product between two sets. So let's suppose that x and y are two sets. Then the Cartesian product between x and y is the set of all ordered pairs where the first component comes from x and the second component comes from y. So for example, suppose x is just the set AB, and y is the set 1, 2, 3. Now, the Cartesian product between x and y, it's going to be the set of all ordered pairs, so all pairs where the first component comes from x and the second component comes from y. So it's going to be the set of all pairs A1, A2, and A3, and then B1, B2, and B3. So that's what the Cartesian product is between x and y. Now, a relation is simply just a subset of the Cartesian product. So you look at the Cartesian product and you identify some pairs that are interesting or that are in the relation and other pairs that are not actually in the relation. We will write, if R is a relation on X, so this is also a new piece of notation. I say here R is a relation on X. All I mean by that is it's a relation between X and itself, so between X and X. So that's why R is a subset of X cross X. We write XR X prime if the pair XX prime is in R, and we'll say not XR X prime, or we'll write XR with a slash through at X prime if that pair is not actually in R. There's also another piece of notation or a way of representing relations that will be useful. If x is related to y, so that just means the pair xy is actually in the relation R, you can represent this graphically by drawing two dots, x and y, and an arrow from x to y. Okay, so the arrow from x to y means that x is related to y, and x is the first component and y is the second. So x is on the left and y is on the right. All right, now what we're going to be interested in, we'll study throughout the semester, are a number of different properties of orderings. Here I use the word ordering to just mean the same thing as a relation. So orderings or relations. So a relation is reflexive if every element is related to itself. Okay, so graphically what this looks like is every element A can see itself. Okay, so every element in the set is related to itself. A relation is said to be complete or satisfies the property of completeness if for any two pairs of elements, so for any pairs of elements in X, it's either the case that they're related, they have to be related one way or the other. So for any two pairs, A and B, either A can see B or B can see A, or actually they were not two distinct objects, they were just one distinct object, A equals B. Okay, so completeness means everything has to be related to something else. Transitivity, this will be a crucial property that we study. This says that if A is related to B and B is related to C, so it takes two steps to get from A to C. Well, in fact, we can get there in just one step. Then it has to be the case that A is related to C. Okay? So an example of a transitive relation is taller than. If Anne is taller than Bob and Bob is taller than Charles, then it has to be the case that Anne is taller than Charles. The next property is symmetry. So symmetry just says that if A is related to B, then you have to have the reversed arrow. Then B has to be related to A. Anti-symmetry says that if I know it's the case that A is related to B and that B is related to A, then that can only happen in one case. It has to be the case that, in fact, A and B are the same object, okay, or they're the same option in the set X. And then finally, a related property, although it's slightly different, asymmetry. And what asymmetry means is that if A is related to B, so we have A is related to B, then it cannot be the case that B is related to A. So if A can see B, then B cannot actually see A. Okay, so we don't have this. This is like a little cycle between A and B. If we have a forward arrow, then we don't have a backward arrow from B going back to A. Okay, there are two more properties that we want to look at, and these are actually going to be crucial properties that we'll be using and studying and talking about throughout the semester. And the first one is negative transitivity, and this one is perhaps a little bit less intuitive or less well known than the other properties. So what negative transitivity says is that if you have an object A and you know that A is not related to B, and B is not related to C, so if A cannot see B and B cannot see C, then it cannot be the case that A can actually see B, or there cannot be an arrow from A to B. So it's just transitivity, except you put a not in front of each of the parts. Now, by itself, I often find this a little bit counterintuitive or hard to understand, but there's an equivalent way of stating transitivity, and it runs as follows. It says that for all A and B, if I know that A is related to B, okay, so I know that I have a comparison I can make between A and B, then that tells me for any other element X, so if you have any other element X here, it must be the case that either A is related to B, or I'm sorry, either A is related to X, or B is related to X. So if A can see B, then it's either, for any other object, either A can see X or B can see X. So why is it the case that this property is just equivalent to negative transitivity? Well, actually, this follows from some very, very simple logic. Just to remind you, there are two sort of logical rules that we'll use here. The first is contraposition, which is if P implies Q, this is equivalent to not Q implies not P. And secondly, we have if it's not the case that P and Q is true, that's just equivalent to saying not P or not Q. So this is just a reminder of the logic that we'll be using. Now, what negative transitivity says is if A is not related to B and B is not related to C, then A is not related to C. Now, using contraposition, if you treat this is going to be the statement P and this is going to be the statement Q, this statement is just equivalent to saying it's not the case that if A is not related to C, then it's not the case that A is not related to B and is not related to B and B is not related to C. Okay, if it's not the case that A is not related to C, that's just equivalent to saying A is related to C. And now we use the second property, this is called De Morgan's law. If it's not the case that this is P and this will be Q, if it's not the case that P and Q is true, that's equivalent to saying it's not the case that A is not related to B, or, so this upside down, this V here stands for or, it's not the case that B is not related to C. All right, so this just simply becomes reducing. If it's not the case that A is not related to B, that means A is related to B, or B is related to C, because again, if it's not the case that B is not related to C, that's just equivalent to B is related to C. So this just tells us that there's an easier or equivalent definition for negative transitivity. The next property is being acyclic. And acyclic, you can think of it as just a generalization of asymmetry. So asymmetry says that if A is related to B, then there cannot be a cycle back. There cannot be an arrow pointing back from B to A. Being acyclic just generalizes this to any sequence of elements. So if A1 is related to A2 is related to A3, and so on, all the way down to AN, then we know there cannot be an arrow from AN back to A1. So this concludes our discussion of basic properties of relation. In the next part, we're going to talk about preferences and how we talk about preferences in this book.